Okay, we have a little bit more to do in Chapter 1. So equations for equations for plane distance problem, and the little n-dimensional geometry, new coordinate system. So equations for plane distance problems. So coordinate equations of planes. A plane pi in our case is determined uniquely by the following geometric information. A particular point in the plane and a particular vector which is perpendicular or normal to the plane. So in other words, if I know a point is in a plane and I also know that this vector is normal to it, how many different planes can satisfy those two conditions? Only one, right? So that's one way to specify a plane. So point P, x0, y0, z0, and the vector n, which looks like some vector, okay? And n is normal, perpendicular to the plane. In other words, pi is the set of all points p, x, y, z. Now, you notice that this is common. We always do that. So if you put a subscript on it, it means that you're talking about a specific point. If you don't, you mean this is kind of free to change. So we're doing that here. In other words, pi is the set of all points. So it's not just one point. Set of all points in space such that P0P, so here's a point P, and here's a point P0, so P0 is in the plane, and if we choose any other point in the plane, and we consider the vector from P0 to that point P, n has to be perpendicular to that. So if you have a point P that satisfies that, that is, if when you go from P to P0, that the vector that connects those 2 points, if that's perpendicular to n, then P is in the plane. Okay? So that's a way to specify the plane. In other words, pi is the set of all the points that satisfy that. That is that n dot P sub 0P equals 0. Remember, when you take the dot product, the only time that you get 0 is if the two vectors are perpendicular. Remember, it has the cosine of the angle there, the cosine of theta in the formula of the dot product. That's one way to express the dot product, is with the cosine of the angle in the formula. And the only time the cosine of the angle is 0 is if the two vectors are perpendicular. So if they're perpendicular, then P must be in the plane. The vector from P0 to P, so P must be in the plane. So we can use this as the equation for the plane. Any point P is in the plane if this is true about it. Now we named P like this, and we named P0 like this. So we can write P0P as x minus x. Remember that that's called the displacement vector. It's just x minus x0. So this one minus this one, and then y minus y0, and z minus z0. Okay? So you can write it like this. That's P. I'm sorry. That's the vector of P0 to P. So if you want to write this, it's n times that, n times this, and we define some vector n, so this is n dot that equals 0, which then can be written like what? The dot product is what? It's a times this plus b times this, and so on, which is what they have here. So this equals 0. So this is another expression. So in other words, if P is this point, and we want to know the equation of the plane, we want to know for an arbitrary point P, is it in the plane or not? So if this is true, for that arbitrary point P, then it's in the plane. So this is also the equation for a plane. So we can write it this way, we can also write it this way. But then you can collect all the constants, right? A times x0 is part of the constant, B times y0 is part of the constant, C times c0 is part of the constant. So you just collect all that and call that D, or whatever. Anyway, you can get the constant part over on the right-hand side. You just have ax, by, and cz on the right-hand side, and everything else moved over to the right-hand side, and call that D. So this is another form of the equation of a line, where D equals this stuff here. So let's try an example. So suppose we have a point, that's our P0, P sub 0, and we have a vector that we want the plane to be normal to. So we want to get the equation for this plane, for the plane that has that goes to this point and is normal to that vector. So we just do this dot this. That is this here is P sub 0, or is it P0 P? Because it's P0 P. This part here is P0 P, and this is N. We just do their dot product and equals 0, and then we multiply it out. We get this, we get this. So this is the equation of that plane. So then they say this is kind of an if-then situation. I'm sorry, an if and only if situation. In other words, not only does a plane in R3 have an equation of this form, but conversely, any equation of this form will describe a plane. Moreover, it is easy to read off the components of the normal vector to the plane from such an equation. So can you see that? Here's our equation of the plane. What was the normal vector though? It was this. So look what happened. It's unlikely that this is a coincidence, right? 2, 2. -1, -1. 4, 4, right? It's unlikely that that's a coincidence. You can just when you see this, you know the normal vector, the vector normal to the plane. It says there just the coefficients of x, y, and z. So given the plane with this equation, find a normal vector to the plane and identify 3 points that lie on the plane. So the normal vector is going to be what? 7, 2, -3. 7, 2, -3. And in fact, they say any non-zero scalar multiple of this will also work, right? Still in the same direction. If you multiply n by 5, so you multiply all these by 5, that's still normal to that's the same direction as n, so it's still normal to the plane. Okay. Now we want to find 3 points in the plane. So we have this equation up here. They say let y and z equal 0. And we get 7x equals 1, so x equals 1, 7, so that's 1 point in the plane. Next, let x and z equal 0 and solve for y, then we get that. That gives us another point, and you can get another point. So we got 3 points in the plane. Okay, another example. So set up the coordinate axes of R3 in the normal way, so that the z-axis points up vertically. That's just the normal way that we set up the axes. Then a plane in R3 is vertical, so you can imagine what's meant by a vertical plane, right? Up and down. If its normal vector n is horizontal, i.e. if n is parallel to the xy plane, horizontal, right? This means that n has no k component. So n can be written follows from equation 2 that a vertical plane has an equation of the form like this, because it doesn't have the k component that we saw before, equation 2. Here. So there's no k component, so this part is 0, so we only get these two pieces here. Okay? So that means that an equation of, the vertical plane has an equation of this form. It doesn't have a k component, so it has an equation of this form, a vertical plane. Okay, so that's just a fact that we can kind of remember. And therefore, a non-vertical plane has an equation of this form where c is not 0. So as long as c is not 0, then we don't have a vertical plane. Okay, that's just an observation. Okay, let's try one more. So suppose we have these 3 points. We want to find the equation of the plane that contains them. So there's 2 ways we're going to do it. We're going to do it sort of the simple-minded way, and then we'll also use what we've learned so far. So there are 2 ways. So the first approach is to take the equation of a line, of a plane rather, which is this, and put the points in. So if I put in 1 for x and 2 for y and 0 for z, then I'll get an equation, this equation here. If I put these points in, these coordinates in, I'll get this equation. And if I do this one, I'll get this equation. So now we have 3 equations, and we have 4 unknowns. They make the remark that there's either no solution or else infinitely many solutions, but we know that there has to be infinitely many solutions because these 3 points must lie on some plane. So we can just go ahead and try and solve this kind of in a mechanical way. We have 3 equations, 4 unknowns. We can solve it going through these steps. So you can check these steps, and we end up with this, and we can set b to be anything, and that will give us an a, b, and c, and then we get the equation here. Okay, so the second method, she says, is cleaner and more geometric, and we want to make use of equation 1. So what was equation? Remember, equation 1 said that if you have a normal vector and you have a point, then this will give you the equation of the plane. So we need to know the coordinates of a particular point in the plane. She says that's no problem. We actually have 3 points, so we can choose any of them, and we need a normal. How do we get a normal? So do you have an idea of how we can get a normal? So we'll use the cross product, because we can easily generate, since we have 3 points, P0, P2, and P1, we can generate 2 vectors in the plane. So then we can take the cross product of these 2 vectors and get a normal to these 2, and therefore a normal to the plane. So that's what we do. So P0, P1, P0, P1, go back and check, and you'll see, well, let's go back and check the points. So here are the points, and so to get P0, P1, here's P0, P1, we can do 3 minus 2, we've got 3 minus 1, and 1 minus 2, and 2 minus 0, so that gives us this, and then we can do a similar thing for this one. And then we want to take the cross product of these 2, and we have to remember how to do that. So remember, we put this one in the second row, and this one in the third row, and then we put ijk up top, and then we have to do the determinant, and after you do all the work, you end up with this, and this is therefore a normal So now we have a normal, and we need 1 point. We actually have 3, so we can just choose any of them. So they take P0, and we do the dot product of P0, which is, sorry, not the dot product of P0. We take P0, so that number P is any point, so it doesn't have a subscript for its x, y, and z, which is what we have here, x, y, and z. So it doesn't have subscripts. And then this is the ones we subtract to get this. And here's the normal. We do the dot product equals 0, and we just multiply this out to get this. And this is the same equation, basically, that we got in doing it the sort of more, the less sophisticated way. Okay, the next example is, suppose we have 2 planes defined by this equation and this equation. We want to get a set of parametric equations for their line of intersection. So they're going to intersect in some line. Usually 2 planes will intersect in some line. And we want to get the parametric equation for that. Let's jump back to, I think this is section 1.2, to parametric equations of lines. Just quickly take a look at that again. So we can write equations for lines like this, but we also saw that we can write equations for any curves using a third parameter, t. So we have x as a function of t and y as a function of t. And if we're in R3, we'll have z as a function of t. And we saw this example that if x equals this and y equals this, they're both functions of t, then you're going to, as t changes, x and y will change, and actually the path that you'll get is a circle. We said that before. And so these 2 equations together can be called the parametric equations for this circle. And remember, the parametric equations are not unique. You can have other equations which would also be parametric equations for the circle, for the same circle. And this was just to say that if you're in R3, you would have parametric equations like that. So next we said that how to provide equations for lines, or parametric equations for lines. So first convince yourself that a line in R2 or R3 is uniquely determined by 2 pieces of geometric information, a vector whose direction is parallel to that of the line, and any point lying on the line. So we saw this is reviewing. So if we know that the line is parallel to A, and we know that P is on there, there's only one line. In fact, P sub 0 is on there. There's only one line that will satisfy those 2 conditions. And then we had this picture, which we said, suppose we have a point P, and we know that the line is going to be parallel to A, or in the direction of A, and we want to get an equation for any other, did I say P? I hope I said P sub 0. Suppose we have a point P sub 0, and for any other P on the line, we want to find the equation for any other P on that line. So we can write this as, we can talk about OP, call it R. So we can say that if P is on the line, then you can say that R is equal to this vector plus some multiple of this vector if P is on the line. If P is not on the line, then like if P is over here, that won't work. You can't say go to here and then write a multiple of A and get something out here. But if P is on the line, that will work. So proposition 2.1 says that. It says this, that R equals this, and we can call this, since P is a kind of free variable, we can call this the vector parametric equation for the line through the point to this point, whose position vector OP sub 0 equals this, and is parallel to some vector A is equal to this. Okay, so we have that. So let's go back to here, and we want to find the parametric equations of planes. So another way to describe a plane in R3 is by a set of parametric equations. First, suppose that A and B are two non-zero, non-parallel vectors in R3. There's two vectors in R3, they're not zero, and they're not parallel. Then A and B determine a plane in R3. I'm wondering why it has to be non-parallel. Seems like if they're parallel, they still determine the plane, but I'm not sure. Anyway, we're assuming they're non-parallel. Okay, so then AB determine a plane in R3 that passes through the origin. I'm sorry, these two vectors are both originate at the origin. So then they determine a plane, and they determine a plane. I guess if they're parallel and they both go through the origin in the same line. Anyway, they're non-parallel. So, so to find the coordinates of a point, P, X, Y, Z, remember this is the 3 points in this plane, draw a parallelogram whose sides are parallel to A and B, and has two opposite vertices at the origin and at P, as shown in figure 1.74. So here, the parallelogram, and we have this, in the parallelogram we have this vertex and the opposite vertex P, and they're both in the plane. So next they observe that there must exist scalars S and T, so that the position vector of P, where's P again? Here's P. So there have to be some S and T that you can say, you go a certain amount out in this direction and then a certain amount down in this direction, and you'll get to P. So in our linear algebra class we would have said that since P is in the span of A and B, the set A and B, then P can be written as a linear combination of A and B. Here they say that OP, from the origin to P, can be written as some S times A plus some T times B. And then the plane may be described as the set of all X in R3, set of all points in R3, such that X equals SA plus TB. So it's basically the span of these two A and B if we use the language of linear algebra. Otherwise, you can just see that this is true. Okay, next, suppose we seek to describe a general plane, one that does not necessarily pass through the origin. So now we have just a plane, doesn't necessarily pass through the origin. So let's suppose that we have to have a point in the plane, and suppose we have two vectors, let A and B be two non-zero, non-parallel vectors that determine the plane through the origin and parallel to our plane. By parallel translating A and B so that their tails are at the head of C, so we just take A and B, they originally originated at the origin, but now we just translate them by the amount of vector C, so that now they're sitting in the plane. We can adapt the preceding discussion to see that the position vector of any point P here in this plane can be described as OP as SA plus TB plus C. So we just sort of move everything up like that. Summarize, a vector parametric equation for the plane pi containing the point P0 and whose position vector is that, and parallel to the non-zero non-parallel vectors AB is this. So we have this, we have this. So here we had a vector OP, but here we're just saying we have X. And this gives us parametric equations as well. We read off the components. Remember, X is a vector in R3. A, B, and C are vectors in R3. So we just set the I, J, K components equal to each other. And we get this equation, and this equation. And these are the parametric equations with two parameters, S and T, for a plane. So they say compare formula 10 with that of equation 1 in proposition 2.1. We need to use two parameters, S and T, to describe a plane instead of a single parameter, T, that appears in the vector parametric equation for a line, because a plane is a two-dimensional object. Okay, the distance between a point and a line. Okay, we'll do this one, but we will skip distance between parallel planes, so I'll let you look at that yourself. And we will skip distance between two skew lines. So skew lines are lines that don't intersect and they're not parallel. But I'll let you go through this one yourself. But let's go through this one together. So the distance between a point and a line. We find the distance between the point 213 and the line. Okay, now we're giving the equation of the line in its vector equation, like this. So, method 1. From the vector parametric equations for the given line, we read off a point B on the line, namely 2, 3, negative 2, 2, 3, negative 2, and a vector parallel to the line, so we use this vector. Using figure 1.76, so we have this vector A parallel to the line, and we have this BP here, BP0 here. So P0 is the point, and here's the line, and we want this distance. So B, we need the point B on the line, so we can just choose this point to be because that's on the line. And we need the vector A, so we have that. And now we want to know the distance from here to here, but you know that if you take the projection of this vector onto this line, you get this. You get this here. But that's not what we want. We don't want this. But if we know this length, and if we know this vector, and we know this vector, then what do we know? We know that, I always get confused about the direction of this, but we know that this vector here, I guess actually the direction won't matter really in this case, but we know that this vector here is what? I guess it's this minus this, okay, is that right? So to make sure that this is right, we're saying that this thing can be expressed like this. So that means that if we take this plus this, of course we should get this, so is that right? So if I take this plus this, which is this part here, the projection, so if I take this whole thing, which is this, supposedly, and I add this to it, I take this plus that, I should get that. So that's right. If I take this and add the projection to it, then the adding and subtracting the projection cancels out, and I end up just with what I wanted, which is this. Okay, maybe you have to figure that out for yourself. But that will give us this vector, and then all we want is the magnitude of this vector. So we have to work out this stuff, but we see that this is what we want, the magnitude of this. So I guess first we need BP0. BP0 is this minus this, I guess. Because here is B, right? That's what we said B was. And here's P0. So we can do that, and we get this for BP0. Now we have to get the projection. We have to go back to our formulas for the projection. So I won't scroll back to the formula, but you can, well, I will scroll back. So scrolling back, this was equation 5. First, remember, we had the magnitude of it somewhere else, which was somewhere here. The magnitude of it was given by that. We did that first. Then we got actual representation of the actual projection itself, which was this, a dot b over a dot a times a. So using that, we do this here. So I guess this is b. And that. So then we get this. We just fill it all out, and we get that the projection is this. Okay. Now we have to do this minus the projection. So we have to do that minus the projection. So we do this minus that. We can check all of this. And we get finally the square root of 5. Okay, so that's one way to do this. And in this case, method 2, they're going to do the same thing. They're going to use trigonometry. So I'm not going to do that one, but you can look at it. Okay, I'm also not going to do example 8, and I'm not going to do example 9. You can do those. Okay, so for homework in this section, 1, 3, and 5, and number 25. Okay, the distance between the point and the line. Now, that's an optional one. If you want to do it, you can. Actually, there are a lot of kind of interesting problems here, but I'm not sure you have time to do them. But you could go and try and do it several of these, but I'm going to make this optional. So just 1, 3, and 5.